We're very happy to have Suvrat Raju today with us. Suvrat received actually his PhD from Harvard in 2008 in string theory. So he's a theoretical physicist with broad interests in anything ranging from quantum field theory to quantum gravity, black holes, obviously. And he's right now in the faculty at the International Center for Theoretical Sciences at Tata Institute in India. Today he's going to tell us about the new perspective on black hole information. Take it.
Okay, thank you very much, Achilles and the organizers for inviting me and to speak today on this momentous date in the United States. So I'm sure some of you are concerned about the events that are happening in the broader world. So I'm going to try and keep you distracted for about an hour or so. So I hope I succeed at that. So I'm going to speak today about work that was mostly done in collaboration with Alok Ladda, Siddharth Prabhu, and Pushkal Srivastav. But also some more recent work with Chandramouli and Olga, and some older work with Shovik, Jan William, and Kyriakos. Since this is, I know, a broad audience, I just wanted to start by showing you some pictures and trying to give you the broad sense of what I'm going to try and tell you. So the broad message that I'm going to try and convey in this talk is the following. The claim is, and I'll make this precise, this is just a cartoon right now, is that in a theory of quantum gravity, if you have a geometric configuration of this kind, where you have some region R, which is surrounded completely by its complement, and the complement extends out to infinity, then a copy of all the information that is available in R that can be probed by quasi-local operators in R can also be probed by quasi-local operators in this complement. And just to emphasize how different that is from a local quantum field theory, this is roughly the same as saying that in a local quantum field theory, we think that we are allowed to specify the wave functional of different parts of a Cauchy slice separately. So we could have this region R and its complement R tilde, and it's possible to put some excitation inside this region R without giving the observers outside who live in R tilde any inkling that this excitation has been placed there. And of course, these observers could wait for some time to allow signals from this excitation to emerge from this region R. But the claim I'm trying to make is that in a theory of gravity, not only do these observers outside know that this excitation has been placed here, they can even discern the precise kind of excitation that has been placed inside this region R. So the claim is that quantum gravity localizes information very differently from local quantum field theories, and that's the LQFT here. This is a cartoon, but I'm going to try in this talk to explain briefly how this can be made precise in at least one setting. There are other settings also if you could make this precise, but at least in one setting I'm going to try and discuss is the setting just a four-dimensional asymptotically flat spacetime, which is some kind of approximation to our world. And what I'm going to try and tell you is that in a universe of this kind where you have quantum gravity, you might have thought that all the information about massless particles in this universe is available on all of null infinity, and that's this cone that I've drawn up here. But I'm going to try and tell you that in fact all this information can also be obtained by observations on the past boundary of future null infinity, and that's this thick red line here, or alternately the future boundary of past null infinity, and that's this thick orange line here. So in a local quantum field theory, you would need to make observations on this entire patch of null infinity. And I'm going to tell you that in quantum gravity, you can squeeze that information down, or all the information is available in this little region here. And when this is applied to black holes, and that's going to be the last part of what I'll say, it gives us a new perspective on black hole information because it suggests that the exterior region of the black hole always contains a copy of the information in the interior without waiting for the black hole to evaporate. So that follows from the claims I made previously, and I'll try and make this a little sharper as well as we go along. Since this is a broad audience, I thought, rather than starting with the most general statement, I would spend some time in the talk today on just trying to work out what I said right now in a very simple example in perturbation theory, where I think we can just follow everything. And then I'll try and make the more general claim I mentioned about 4D flat space. I'll try and say it as concisely as I can. And then I'll go on to talk about black holes. I already did this first part, which was the introduction. Okay, so let me start with just some very simple example of how, this claim I made, this surprising sounding claim that all the information is always outside a region in gravity can be checked and can be verified in one example in perturbation theory. Before I start doing that, I just want to remind you of some very basic things. This is, we already know, I mean, all of us know and agree that there is at least one way in which gravity is different from other theories. And that simple way is the fact that gravity obeys a Gauss law. And so that means that if you place some excitation, you place some object somewhere here, you can go very far away and you can measure the mass of that object. You can measure the energy of that object. And this is already one way in which gravity is different. And since all excitations have energy, there's really no way to put some excitation in the middle here without changing at least something far away. Okay? Now, usually, when we learn general relativity, we of course learn this fact. But the way we think about this is that, there is a Gauss law, but the Gauss law tells us about one number. It looks like it tells us about the mass. And if you have a spherically symmetric configuration, you could take this compact ball of dust, or you could take this dilute ball of dust that you see on the right-hand side. And just by Birkhoff's theorem, you could make the metric identical and make it exactly the Schwarzschild metric outside this region where the matter exists. And in fact, there's a more fancy theorem by Corvino and Schoen, which proved about 20 years ago, which points out that you can do this even in more general configurations, which are not spherically symmetric. You can always make the metric just identical, metric of two configurations identical outside some large ball, and the same inside that ball. Okay? But I want to point out that already at this stage, it's clear that quantum mechanically, we get a little bit more than one number. And the reason we get more than one number is that if you think about how in a quantum mechanical system, you would make up this compact ball or this dilute ball, you would have to do it by superposing some number of energy eigenstates or some number of eigenstate excitations of the field that makes up these balls. And these eigenstates are all delocalized, and so you have to superpose them in a way to make up either this ball or this kind of a ball. And therefore, you have to take some state of this kind, some superposition of energy eigenstates. And then you already see that if you try and measure the energy as a quantum mechanical operator, you can measure more than the expectation value of the energy. You can measure higher moments of the energy. So you could measure in this state the expectation value of h to the power q, and that is not the same as the expectation value of h to the power q. So you could, if you first raise to the power and then take the expectation value, that's not the same as taking the expectation value and raising to the power. Whereas in the classical theory, these things would be the same. There is really no information in the classical theory that goes beyond the expectation value of h. But in the quantum mechanical theory, you see clearly that these different moments give you more information. And moreover, you could also take correlation functions of the fluctuations in the energy with other dynamical fields. So if this ball of dust was made up of some scalar field, you could try and measure just far away on this Gaussian surface, you could try and measure correlators of the Hamiltonian and this other field. And these correlators are different from just taking the expectation value of the Hamiltonian and taking the expectation value of this field, which is what you would have done classically. And so you already see that in a sense, quantum mechanically, there is more information than just one number in just the simple fact that the energy can be measured far away. In fact, I want to tell you that there's a lot more information, and I want to explain how you can see this at least in detail in one simple example in perturbation theory. So the example is of the following kind. So here is our four-dimensional Minkowski space. And let's say the vacuum state is 0. I'll mention the degeneracies in the vacuum and so on. But for now, let's just think of some vacuum state. Let's call it 0. And let's think of some dynamical field, which is n. This could be a component of the metric, or it could be some scalar field. And you could take you could take this field and you could put it inside a unitary operator, and you could make some excitation, which is some excitation of this field on top of the vacuum. Now, this excitation is labeled by this function f of u omega, where this coordinate u is the coordinate along future null infinity. And I'm going to take this function f to be localized near u equal to 0. So it's localized somewhere here. Okay? So what the state means physically is pretty clear. It means that you have a vacuum, and on top of the vacuum, you have one pulse of some excitation, some field, or some metric. And this pulse is going to come and hit null infinity somewhere at u equal to 0, which is the middle here. Okay? Now, the challenge, I said that the information is always outside. So let's say we have some astrophysicists These are my astrophysicists, the ones who live here. So these astrophysicists live far away near infinity. And the challenge is that at small lambda, so I'm working in perturbation theory, they have to measure some correlation functions in this little red region. Okay? So they need to measure correlation functions near u goes to minus infinity in this red region, which is well before the pulse of excitation came and hit null infinity. So the challenge is they need to measure these, they need to measure whatever they want to do in this red region, and they need to figure out not just the mass of the excitation, which we all agree one could figure out, but they need to actually determine the form of this f of u omega. So they need to determine the profile of this excitation that's going to come and hit you. And that contains a lot more details than just the mass. It tells you, for instance, if the excitation is dilute, if it's spread out over a long period, or if it's a short and sharp excitation. Okay? So that's the setup that I'd like to examine. And this is a setup where one can already see how these correlators that I mentioned allow you to extract information in gravity in a way that's not possible in the classical theory. Okay, so it turns out that the correlators we need to do this, the correlators these astrophysicists need to do, is just measure in this. So they're living in this excited state, right? They're living here, and there's this excitation that lives here. And it turns out that the correlators they need to measure are just quantum correlators of the energy, this energy h, with the dynamical field which creates this excitation. But they need to measure these correlators near u equals minus infinity. So I'm just going to measure this 2-point function in this range from u equals minus infinity to minus 1 over epsilon. And of course, this h itself is an operator in this red region because it's an integrated metric component near the past boundary of future null infinity. So it's actually an integrated metric component near u goes to minus infinity. So you see clearly that this correlator I'm asking them, these astrophysicists, to measure is just a 2-point correlation function which is localized in this little red region. And it's well before this pulse is going to come and hit null infinity. So now it's a simple calculation to compute what this 2-point function would be in this excited state. And you can do the calculation. It's a pretty simple calculation. The way it works is that you take this function f and you expand it out, and you can check that this h acts like a d by du. And so once you do the calculation and you put all the factors together, you find that this 2-point function gives you the following form. Okay? So the first thing to note is that this 2-point function is not zero. Okay? There are some fluctuations of the energy which are correlated with fluctuations of the scalar field here. And what this 2-point function is actually this function f, which controls the profile of this excitation, smeared with some kernel, which is x minus u minus some I epsilon, which is the some I epsilon prescription, and integrated over x. Okay? So remember, this f of x has support only near x equal to 0. Okay, that's here. But this 2-point function has a signal all the way here near u goes to minus infinity. And this is just something that you can check. And this is the precise form of the signal that you get by looking at this 2-point function. Now you can check actually that formally, if you know this 2-point function for some range of u from minus infinity to minus 1 over epsilon, you can prove formally that you can reconstruct this entire profile f. But in fact, there's a simpler way to just see it directly. If you just look at this function, remember that f has support near x equal to 0. And so if you just series expand this denominator in powers of x by u, because remember u is near minus infinity, so the mod of u is much larger than the mod of x, and so you can do a series expansion. You see that every term in that series expansion gives you a moment of f. The first term gives you the integral of f, the second term gives you integral of x of f of x, the third term gives you x squared f of x. And so you see by doing the series expansion, you will get all the moments of f, and therefore you can reconstruct the full profile f and not just the mass of this excitation. Okay? So this is an interesting example, but you might say, well, okay, you did this case, but what if I give you something harder? What if you have two identical fields, and maybe these identical fields have a global symmetry? So maybe there are no global symmetries in gravity, but we don't have to assume that. Maybe we have two identical fields, phi1 and phi2, which are completely identical. And then I send you pulses, one which is made of the field phi1 and the other which is made of the field phi2. So that's the blue pulse and the green pulse. And ask you to identify these astrophysicists again, to identify while they're sitting in this little, far away at infinity and making observations in this little red band, whether the pulse was the blue pulse or the green pulse. So in fact, it turns out they can do precisely the same thing. And if you just think about what we did previously, in the state F1, where the pulse was created by an excitation of phi1, the correlators of h phi1 would be not 0. In fact, they would be what we worked out previously. But the correlators of h with phi2, the fluctuations of h with phi2 would be 0. Whereas in the other case, if the excitation was made of the field phi 2, then the correlators of H with phi 2 would not be 0, whereas the correlators of H with phi 1 would be 0. So you see that just by measuring these 2-point functions, H phi 1 and H phi 2, these astrophysicists can figure out which of the two fields was used to create the excitation and also what the profile of the excitation was. Okay, so now let's do some sanity checks. It's pretty important that this method doesn't work without gravity. So you might have thought, in gauge theories, we have long-range gauge charges, so why can't I do something similar and, violate, this notion of localization of information in gauge theories? But you can't, because any non-gravitational gauge theory contains exactly local gauge invariant bulk operators. So for instance, if I took the state 0 and I took this excitation to be made out of e to the I trace of f squared at u equal to 0, and I thought of these two states, the astrophysicists here, if they were not allowed to use gravitational effects, would be completely defeated, because every observation they make in this red band would commute with this unitary operator, and therefore every observation they made here would be the same as the observation in the vacuum, and there is no way they could determine whether the state was this one or this one without waiting till u equal to 0 to see what the state is. Okay? In fact, it's important that these effects also go away in the classical limit. So this is the only time in this talk I'm going to restore factors of h bar and c. But if you were to restore factors of h bar and c, you would see this correlation function that I inserted comes with some factors of h bar squared into g divided by c squared. And what this tells you is that if you were to take either g Newton to 0, which takes you to the non-gravitational limit, or you were to take h bar to 0, which takes you to the classical limit, this correlation function just vanishes. And therefore, this is consistent with the fact that in the classical theory, the observers here cannot obtain information about this pulse, whereas in the quantum mechanical theory, they can obtain information. And so this is a consistency check that the usual notions we have, that the Gauss law just tells you about some total energy far away in the classical theory, is correct. And that's consistent with the fact that quantum mechanically, it could tell you more. Okay, so now I gave you an argument in some special states, and you might think, I used the fact that I had some very special simple states to identify them. I now want to sketch for you, I won't go through this in detail, but I'm happy to do so in the discussion section, a proof that this argument always works. Yeah.
So can I ask a quick question about the perturbative calculation?
Yes,
so
sure.
is there an order of limits thing? So your interval near scribe plus minus can be arbitrarily small, or right? So what's the interplay between lambda and epsilon?
Yeah, this interval is actually, well, it's drawn as small in the Penrose diagram. It's actually a semi-infinite interval because it goes from u equals minus infinity to u equals minus 1 over epsilon.
Yeah.
So it looks small in the Penrose diagram because u equals minus infinity is crunched up here. But it needs to go from minus infinity to minus 1 over epsilon, but you could take epsilon to be as small as you like. So it just needs to be, you need some finite number for this argument to work, but you just need some finite number.
But if I take epsilon to be order lambda, this perturbative argument.
Oh, sorry, there are two confusions. This epsilon, by the way,
not
is
this
just
epsilon,
an
the one in 1 over epsilon.
I don't think that matters. You could take epsilon to be order lambda. You're worried that you'd get confused in the series expansion?
Yes, in this perturbative argument, there is an order lambda expansion, and then there is your interval.
There's an order 1 over u expansion, but remember, u can go up to minus infinity. So, if you're saying u goes from 1 over lambda or minus 1 over lambda to minus infinity, you can still extract all these series expansions by making observations at different values of u. So you need to make observations at different values of u. I have to give you this correlator for all values of u from minus infinity to some point, which is minus 1 over epsilon. And if you do that, you can just show that you can get everything. It doesn't matter what that point is.
Isn't there a worry, though, if epsilon is less than lambda? I think I agree with him, because you had a power series expansion 1 over u to a power, right? So as I take u to infinity, those terms become vanishingly small. So do you have to just wait a really long time? I mean, it sounds like they would be harder to decouple.
You're worried about how you decouple these things. Oh, you're right. You'd have to. Thank you very much. So you'd have to decouple it in this thing to be able to extract. You see, I kept this lambda term, but there are these order lambda squared terms which decouple. So you'd have to, of course, allow them. You'd have to give these observers access to a family of states with different powers of lambda. I'll in fact tell you something right now where you don't need to do that. And so they can unambiguously extract the order lambda coefficient and drop the order lambda squared coefficient, and also unambiguously extract these u coefficients. So you have to give them these correlators as a function of lambda and as a function of u. And if you give it to them as a function of lambda and u, they can extract the order lambda piece and also all these powers in u. So, lambda has to be small, so I can take the function, the order lambda piece. I can extract that unambiguously, and then I need to be able to extract the u piece as well. So, it's just the fact that you need these correlators for different values of the parameters, so you can unambiguously extract this term. Is that good? There's an analyticity argument, by the way. If you give me this function for any range of u, it doesn't even have to be near u equals minus infinity. That's actually enough to fix it all over, on all the real line, just because of some analyticity problems. You don't even have to do the power series expansion.
Right. If you can unambiguously extract the order lambda term, then the analyticity argument, will make the argument work for any epsilon.
Indeed, thank you for pointing that out. In this example I gave you, you do need to be able to unambiguously extract out the order lambda term. Otherwise, I would have to do something more complicated, where I would have to keep track of the order lambda square terms and so on. In the next example I give you, I will keep track of all of these terms. I won't do anything in perturbation theory. Okay. So now I want to show you that this example works even if you go beyond perturbation theory. I'll have to give you a formal argument because we can't compute beyond perturbation theory. And I'm going to try and argue for you that if you make some reasonable assumptions about the theory, then any two distinct states of massless excitations, not just these unitary states, can be distinguished by observables near this I plus minus. Okay? So that's the claim that I'd like to make, which is a stronger claim than what I made previously, when I was discussing one family of states which was determined by this function f and this parameter lambda. Okay, so let me just remind you of a few things about four-dimensional asymptotically flat spacetimes and what we understand about them. I'm going to be working with the standard boundary conditions. So in what's called bondi gauge, there's some fall-off conditions for the metric, which have been worked out in great detail. And there are some components of the metric. There are these components which are called the bondi news, which are what you measure in gravitational detectors. And then there are some constraints like the bondi mass, which is some other constraint. And what I'm going to be interested in, I now need to allow these observers in this I plus minus to be able to measure all possible polynomials of this bondi news and this bondi mass. And that's what would be called an operator algebra of all of these operators in this region here and this region here. And if there are other dynamical massless fields in the theory, I'll have to include them in my algebra as well. So they need to be allowed to make measurements of all of these other dynamical fields as well. Okay. Now, we've learned something about the Hilbert space structure of this theory. In fact, many people at Harvard have done a lot of work about this. And the Hilbert space structure of the theory, as far as we understand, is of the following kind. It turns out that there isn't one vacuum in four-dimensional flat space, in Minkowski space and gravity, but there's an infinite number of vacua. And these vacua are labeled by something called the supertranslation charges. And there's an infinite number of these supertranslation charges. And you can label all of these distinct vacua by their eigenvalues under these supertranslation charges. And on top of each such vacuum, you build a Fock space by taking these dynamical fields, these metric or these other fields, and just exciting one of these vacuum. And then the full Hilbert space of massless particles is just the direct sum of all of these Fock spaces. And all the statements I'm going to make are going to be confined to this Hilbert space, which is the Hilbert space of massless particles. Okay. So now there are two arguments. I need to tell you that any state in this Hilbert space can be distinguished by this algebra of operators near minus infinity. And there are two steps. I'm just going to sketch them. The first step is as follows. The first step is that the fact that you have positivity of the Hamiltonian tells you, and this is just a simple fact about this Hilbert space, that these states that you were creating by acting with these smeared excitations at all values of null infinity, these dynamical fields smeared with test functions at all values of u, can in fact be approximated arbitrarily well by acting with operators in this algebra A minus infinity on one of these vacua. So let me try and tell you how the proof goes. I'll give you the proof for one particle states, and the proof for higher particle states is the same. You see, let's say you have some one particle state which is created by acting with n smeared with some test function at some value of u. Think of this matrix element, which is the matrix element between this one particle state n and the vacuum. If you insert a complete set of energy eigenstates in this matrix element, you will find that this matrix element is analytic when u is extended in the upper half plane. Okay? So when imaginary u is taken to be positive, you'll see this matrix element is positive, is analytic. And therefore, if this matrix element vanishes for all u in minus infinity to minus 1 by epsilon, which would be the statement that you had some one particle state that was orthogonal to all states that could be created by the action of this n of u in minus infinity to minus 1 over epsilon, then this matrix element, just by the standard theorems of complex analysis, would have to vanish for all u. But that's not possible because there is no one particle state for which this matrix element vanishes for all u, except for the null state. this tells you that there is no one particle state that's orthogonal to the action of n of u from minus infinity to minus 1 over epsilon. And therefore, all states, all one particle states, can be approximated arbitrarily well by the action of n of u from minus infinity to minus 1 over epsilon on this vacuum. Okay. So that's the first step. And of course, you can make an analogous argument, which involves slightly more intricate complex analysis for all particle states. The second step, and this is actually the part where gravity is important, and as I mentioned, the fact that you had the Hamiltonian at the past boundary of future null infinity is important, is the fact that both the Hamiltonian and the supertranslation charges are elements of this algebra at a minus infinity. Now, the standard result in operator algebras, which tells you that when you have an operator as an element of an algebra, all its spectral projectors are elements of the algebra. But there's a more physical way to see this. You see, if you're allowed to measure the Hamiltonian among these supertranslation charges, you can use a measure in discard procedure in quantum mechanics. You make a measurement of the energy and you discard states where you don't get zero, and that gives you this projector, which is P0. Or you make a measurement of the supertranslation charge and you discard states where you don't get a particular value. And if you combine these kinds of projectors, you can extract a projector onto a specific vacuum, and you show that a projector onto a specific vacuum is an element of this operator algebra near minus infinity. And that's a very unusual property of gravity. In no other theory is a projector on the vacuum an element of a local operator algebra, okay, which is true in gravity. You can also check just from low energy effective field theory that once you have these projectors, you can also you can construct all vacuum operators. So you can construct operators that map you from one vacuum to the other. And these transition operators are also in this operator algebra a minus infinity. Okay. Now, you can put these steps together, and the rest of the argument follows quite simply. You see, you take any operator that maps you from the space of massless particles back to itself, you expand it out in a complete basis of states in these Fock space states that I mentioned. Then by using the first argument I mentioned, you notice that each of these Fock space states can be written as the action of an operator in a minus infinity on one of the vacua. And then you notice that this operator that enters in the middle, this operator which is ket s bra s prime, is also an element of a minus infinity by the argument I just gave you previously. And therefore, everything that appears on the right-hand side, which is this product of three operators, x into t into x dagger, is entirely in a minus infinity because it's just a linear combination of a product of three operators in a minus infinity. And this tells you that any operator from the space of massless particles back to itself can be approximated arbitrarily well by an operator near the past boundary of future null infinity. And since any two distinct states can always be distinguished by some operator, it tells you that any two distinct states can be distinguished by some operator that lives in the past boundary of future null infinity. Now you might have asked, I used some results here which I knew from what we know about the semi-classical theory of quantum gravity, but we don't really know how to do string theory in full four-dimensional asymptotically flat spacetime. So how do I know that these results are going to extend to the full theory of quantum gravity? But if you look carefully at the arguments that I made, I assumed, of course, the positivity of the Hamiltonian, but the other assumptions I made were just assumptions about the low energy structure of the theory. The fact that the vacua were labeled by some operators near the past boundary of future null infinity, and the fact that operators that map the vacua back to themselves are contained in this algebra. So if the full theory shares some low energy properties of the semi-classical theory, it tells you that all information about massless particles is available near this past boundary. And this is a generalization of the perturbative argument I gave you previously. It's a formal argument, but it's a robust formal argument that relies on rather weak assumptions that tells you that you can extract all information from this past boundary, and you can always play this trick that I mentioned previously. Okay, I should mention, I won't go through this right now, is that you could apply the same arguments in ADS and you would find that all information about the bulk is actually present in a small time band 0 to epsilon, where epsilon can be any finite number on the boundary. This is of course consistent with ADS-CFT. We expect this from ADS-CFT, but we don't need to assume ADS-CFT to show this result. In fact, ADS-CFT tells us a stronger result, tells us all information is available in a single slice, not in this time band. And the second thing here is that we don't need to restrict to massless excitations. And that's just a technical point about the way the ADS boundary behaves versus the null boundary. Okay, so now I just want to spend the last 5 or 10 minutes talking a little bit about black holes and what the implications of this for black holes are. So I think that if you think about the results I mentioned about the fact that all this information on null infinity is available on the past boundary of future null infinity, I think it tells you that perhaps one should think about black holes and black hole evaporation in four-dimensional asymptotically flat spacetimes in a slightly different way. And the reason is that one often asks how information comes out of the black hole as it evaporates, because that's the way we think about evaporation and information coming out in local quantum field theories. And that's the question of how one can obtain information from this green slice here. But the results I just discussed previously suggest that the information is also available on this red slice, because that's the thing that gets mapped to this past boundary of future null infinity. And this suggests that by making the right measurements even before evaporation, one would obtain complete information about the state from outside. So there's a slightly more formal way of saying this, and that's the following. You see, it's conventional to define a state on Scri plus by saying we look for some density matrix, which has the property that when it is traced with some other observable on Scri plus, it gives you the right expectation value for this observable. But by the results I showed you previously, since all operators that live on this future null infinity can be squeezed down to operators that live here, you can always choose this density operator to be something that lives in A minus infinity. And since you can just make that choice once and for all, the fact that you expand this state as you go up on null infinity doesn't give you access to any more operators. And that tells you that this von Neumann entropy is just independent of you. And so that would tell you that if you were to compute the von Neumann entropy of this state on future null infinity, you would find that this von Neumann entropy is just flat. So this is in contrast to the argument that this von Neumann entropy should obey a page curve, which is a curve that first goes up and then comes down. But if you look at Page's argument, the argument is explicitly based on the fact that the Hilbert space on this Cauchy slice factorizes into a part outside and a part inside. And that's incorrect in gravity. And you can see that it's incorrect already in the semi-classical theory, as I showed you in the first part of the talk. Now, a question that I often get asked when I say this, and so I should clarify this, is that sometimes people say, is there no way to recover the conventional Page curve? Can't we throw out some observables to make gravity look like ordinary quantum field theory? And I think the answer is yes, and I could try and describe more in the discussion section why the appropriate restriction of an algebra on Scri plus would yield the Page curve. But the point is that if you were to make all possible physically allowed observations in gravity, then the information is always available outside a black hole in flat space, even before a black hole evaporates. And that follows from the results I mentioned previously. Now, perhaps a very natural question is this result only formal? So let me say a few words about that. You see, you might have said, I proved some formal results in operator algebras, and I gave you some perturbative examples, but is this result really a meaningful result? Because in a sense, you could have said that I could have applied this result to some lump of coal which was burning, and I could have said the information about the coal is always available outside. But in fact, there's a distinction between ordinary thermodynamic objects like a lump of coal or like a gas and black holes. And the distinction is as follows. You see, if you take some ordinary object like a coal or like some thermodynamic gas, there is a well-defined sense in which you can keep its entropy finite. So you keep the number of degrees of freedom in the system finite, and you take L Planck to 0. When you do that, you see that the quantum gravity effects I've been talking about become infinitely hard. Whereas the question of reconstructing the microstate of the coal by looking at its radiation is a hard question, but that hardness is determined by e to the minus s, and you can keep that finite while making these quantum gravity effects that I'm talking about infinitely hard. But for black holes, note that this limit does not exist. If you try to take L Planck to 0, s would go to infinity. And so there is no clean separation of difficulty between the difficulty of trying to reconstruct the microstate by measuring the black hole radiation, which requires an accuracy e to the minus s, and by trying to determine the microstate by using these quantum gravity effects that I've been describing in this talk. Let me actually give you a little bit of intuition that you could get about the relative difficulty just by looking at small black holes in ADS-CFT. You see, you could think about this whole process in ADS-CFT, and you could think of a process where you have a black hole which forms from the collapse of some dust, and it's a small black hole. So its radius is much smaller than the ADS radius. And this is the cartoon, this is the dust, and then it would get a black hole, which is very small, and then it evaporates into a gas of radiation, which are these blue dots here. So now in ADS-CFT, we know we can always extract information from boundary correlators. You could extract them at time t1, or you could extract it at time t2 when the black hole forms, or you could extract it at time t3 after the black hole is evaporated. And you could ask in the CFT, how difficult is it to extract or determine the state by measuring correlators at these 3 times? Now, at early times, when the black hole is not formed, the state in the CFT is some bunch of glue balls, which are just well separated. And so low point correlators of some single trace operators are enough to determine the state. And that's consistent also with what you see in the bulk. You have some dust and you measure some low point correlators and you can determine the state. Now, after the black hole is formed, these glue balls have thermalized. So you have a thermal state. And so it's very hard to extract information from CFT correlators, but you can estimate how hard it is. And roughly it requires S point correlators, where S is the entropy of the black hole. And you need to measure these correlators to an accuracy e to the minus S, just because that's the standard estimate for how hard it is to reconstruct the microstate in a thermal system. But now notice what happens after the black hole evaporates, which is at this time T3. At time T3, you again have a thermal system because the system doesn't unthermalize in the CFT. You have some glue balls, they crash, they form some quark gluon plasma, and the quark gluon plasma evaporated back into glue balls. But the system is always becoming more thermal, so its thermodynamic entropy has now gone up to S prime, where S prime is larger than S. And therefore, if you now want to reconstruct the microstate by making measurements at T3, you need to measure S prime point correlators to an accuracy e to the minus S prime. So this would suggest, just the standard arguments from thermalization would suggest it's actually harder in this example to determine the microstate by making measurements at later time than it is at this intermediate time when the black hole exists. I should caution you, of course, that this is not a precise argument. The argument I gave right now is just a crude estimate, but it suggests that, these results I'm talking about are not just formal results, and there is no reason why you would expect that these, to extract information using these quantum gravity effects is necessarily much harder than extracting information by collecting the radiation. Okay, so I'm almost done. Let me just say a couple of words about recent work on the page curve, since that's probably a question I'll get. So of course, there's been a lot of recent work on computing the page curve in evaporating black holes. And I just wanted to explain the contrast of that picture with the picture that I've been describing. So the recent work that's been done almost always considers two coupled CFTs. So you take one CFT, which might be actually a CFT in a lower dimension, and couple it to a CFT in a higher dimension. And then you allow, you take an excited state in the CFT and you allow it to evaporate into this other CFT. So this excited state could contain a black hole, but the division of the Hilbert space that you make is not a division of black hole and radiation. You don't make a division in the bulk. You make a division on the boundary between one quantum mechanical system, a non-gravitational quantum mechanical system, which is some CFT A, and another non-gravitational quantum mechanical system, which is CFT B. And therefore, because these are just two non-gravitational systems which exist in your lab, they might have a dual description as some gravitational systems, but they're just existing in your lab. There's a clear factorization of the Hilbert space. And in fact, it's not the case that CFT A corresponds only to the black hole. It corresponds to the black hole plus some radiation. And CFT B also corresponds to some radiation. And you can make this division neatly on the boundary, and then just the usual rules of quantum mechanics tell you that because you made this division at some place where gravity was non-dynamical, the Hilbert space would factorize, and therefore both SA and SP would follow a conventional page curve. But of course, if you wanted to apply this result to black holes in our world, that's more tricky, because one way to think about these results is that you have a black hole and at some point you just switched off gravity. So you have a black hole and then by hand, gravity is just switched off here. And then you compute the entanglement of this part, which has no gravity, with this entire part that lives here. But that's not the same as thinking of a black hole in our world, where you have a black hole and then you have weak gravity far away. And the reason it's not the same is because the kinds of questions one is asking about the von Neumann entropy are fine-grained questions, and therefore weak effects in gravity can conspire to give very different answers for such fine-grained questions, as I showed you in particular, as I argued for the von Neumann entropy. So I think a plausible story is that in systems where gravity is just non-dynamical, it's literally just switched off beyond some region, the information really emerges after the page time, as it does in a lot of these recent computations. But for more realistic black holes, I think a more valid statement is that the information is always outside. Okay, so I'm going to stop here. This is just a quick summary of what I said. I tried to argue to you, this is a cartoon that in gravity localizes information very differently from local quantum field theories, in that a copy of the information that's inside a region is also available in its complement. And that's this cartoon that's visible here. The observers outside can determine the excitation inside. This can be proved formally under certain conditions, which I described. But the important part, and that was the first part of my talk, is that this is not just some formal result in operator algebras. You can verify this in perturbation theory. I gave you some examples in flat space, but you can verify it in ADS in even more detail, as we did in one of the references I showed you. And so this is something that can be verified by just computing correlation functions in perturbation theory, and it's not a formal result. And I think if you take this result seriously, it provides a fresh perspective on black hole information and tells us that we should think about information in black holes differently from the way we think about information in ordinary thermodynamic objects, which are governed by local quantum field theories. Okay, so I'll stop here. Thank you for your patience.
Thank you, Suvrat. So we have time for questions. You can either raise your hand and I'll give you the mic, or right. So Avi, you have the first.
Yeah. So my question is from a point of view of an astrophysicist. Suppose suppose you were an experimentalist and you were given all the opportunities you can imagine to do an experiment by approaching the horizon. How would you, rather than mathematically prove your point, how would you demonstrate it experimentally? So what do you need to measure in order to demonstrate it?
Yeah. I'm not sure if you're there for the first part of the talk, but so you would need to measure basically correlators of this kind. So let me go back to this example. This example I had in perturbation theory, where I was talking about these excitations. And for these kinds of excitations, I said that you needed to measure these kinds of 2-point functions of the energy with other dynamical fields. These 2-point functions are very suppressed. Let me also show you that they're extremely suppressed in this place where I put in these factors. So they're very small 2-point functions, but let's say you're an astrophysicist with arbitrary powers, so you could just measure arbitrary accuracy. Then you would have to measure not just 2-point functions for black hole states, but S-point functions, where S was the entropy of the black hole, and you would need to measure them to accuracy e to the minus S. So you need to measure.
How do you measure that? Do you measure it by perturbing the black hole, or how do you measure that?
So very good. So you would need a number of identical copies of the black hole. And if you want a precise physical protocol, in some cases, the kind of physical protocol we developed is that you first make a perturbation with some unitary operator, and then you make a measurement of the energy. So you have a number of identical copies of the black hole with you, and you make a perturbation of the black hole, and then you make a measurement of the energy. That allows you to extract these kinds of correlators, and then you combine results across a large number of such systems, and then you determine the microstate.
Okay, so let me put it differently. If you had a small black hole orbiting the big black hole, it's sort of extreme mass ratio in spiral, would the gravitational wave that you get out carry any of these correlations?
Certainly. I think in this case of the small black hole orbiting a big black hole, I mean, this is just I think this is the kind of thing that you would see at much lower points, because now you're talking about two macroscopically distinct states. I mean, if I understood correctly, you're comparing a big black hole with just a small black hole orbiting a big black hole.
So my question is, can you measure something like in the gravitational wave output of this system that would indicate the correlations that you're talking? I mean, you're talking about mathematical correlation producing multiple black holes of the same, but in reality, suppose there is a black hole and you wanted to demonstrate your point experimentally, what experiment would you do?
Or you mean in a single system?
Yeah, in a single system. I mean, yeah, we're talking about the real world. You have a black hole and you want to show that it has the information that you're talking about.
Yeah. So in a single system, actually, it's much harder, and that's just because quantum mechanics is harder to do with a single system. Now, if you just have a single system, you make one measurement, and the measurement is probabilistic. So unless you can find some measurement that gives you some answer with probability 1, you're in trouble. You can't determine the microstate of a system in quantum mechanics.
I see. So there is no hope. There is no hope for an astrophysicist to demonstrate your point.
I don't know if there's no hope, but you would have to think of something much cleverer, where you would have to think of some quantum mechanical operation that gives you an answer with probability 1 in some cases, and you could then apply that operation and see if you would get that probability. In what I'm talking about expectation values, and these expectation values necessarily involve taking a number of identical copies and making measurements on those identical copies.
Thank you.
I'm not saying there's no hope, but it's a much harder question, and maybe for some cases, you could do these things in quantum computing. We try and look for one operation. Yeah.
I mean, the language that you're using is very helpful for atoms, where you have a lot of copies of the same system. But in a black hole case, it's not easy to produce multiple copies of the same system.
I agree. I agree. I mean, of course, from an experimental point of view, if you were to try and compute, for example, what these numbers are, these numbers would be extraordinarily small. I mean, and the entropy of these black holes is 10 to the 77. So, we are talking about things which are, the only hope you would have of doing this is somehow by constructing some other kind of system which simulates a black hole, and then having identical copies of that, and then determining what you could do in that. So that's the kind of thing, if you wanted to measure it experimentally, you could do, which I think is actually not impossible. to try and think of some system that simulates a black hole which you could produce in a lab with some process. But that's the kind of thing you would need to do to measure this.
Thank you.
I mean, not with real astrophysical black holes.
Thank you.
Yeah. Other questions?
So can I ask? So you're referring to some kind of restriction you can make on the operator algebra to give you back the page curve?
Yeah.
So what
I
is,
think, well, okay. So I think the restriction would actually, the restriction, I should say it, yeah. The restriction actually, I think, would be that sorry. Yeah, you would need, I think, but you would need to throw out the bondi mass. If you were to throw out the bondi mass and you look at the algebra null infinity, it has the property that, if you look at the other operators, which are the news operators and other dynamical scalar field operators or gauge field operators, the operator algebra closes and you don't get back the bondi mass. And therefore, I think there's a sense in which you could throw out the important gravitational effect, which was the bondi mass, the energy, and just keep track of the other excitations. And by the way, it's not clear that will give you the conventional page curve, because it's then a question of how much information is available in the soft charges compared to the hard sector. So I mean, if Andy and others have been saying there's a lot of information available in the soft charges, but if you believe that most of the information is in the hard excitations, then by throwing out the bondi mass, you would probably recover the page curve. I just want to say, from a physical point of view, it's slightly artificial, because the way you would measure the metric is by measuring the Riemann tensor, measuring something physical like that. And the Riemann tensor would just, all components of the metric enter into that. But then you could say, after I have measured the Riemann tensor, I just decide to close my eyes to some components of the metric, and I just throw them away. And if you do that, then I think you would probably get back the page curve. Yeah, another way to say it is, the other way, other ways to say it, but yeah, that's one clear way.
I see. Thanks.
Okay. Anyone else? Okay, I don't see a raised hand. Maybe I can ask a question myself. Is there any sense of, so you told us that in the theory of quantum gravity, the information that exists on an entire Cauchy slice also exists near its boundary. Is there a statement in an appropriate semi-classical statement in which there would be some kind of sub-region statement, like part of the information on the Cauchy slice exists?
Yeah, I think
what is
it's
that?
A great question.
That
it's a great question, but I don't know the answer. I mean, you would need some, you'd like some analog of sub-region duality in ADS CFT. But you say, you give me a region on ADS on the boundary, and I get like a sub-region in the bulk. So I think that's a great question. I would love to know the answer, but I don't know the answer. I really think that's a very interesting question. Is there an analog of sub-region duality? I think it should be possible to answer that question, but I don't know what the answer is.
Okay. Right. So I don't see any raised hands. If you want to ask a question, you can just go ahead and unmute yourself and ask it. Going once, going twice. Okay, I believe that's it. Let's thank Suvrat again. Thank you very much for a very interesting talk.
Thank you. Thanks.
Good luck. Vote. I'll see you all next week.
Okay. See you. Thank you.
Bye-bye.
Yeah, see you. Bye.